we're going to look at projecting vectors onto other vectors. We've kind of seen it before, because essentially when we break it up into components, you remember how we, one of the ways of looking at a vector was in components, so much horizontally, so much vertically. Well, that essentially is projecting the vector onto the x-axis and the y-axis. So there's the vector OP. We know it's got magnitude of 2. It makes an angle of 30 degrees with the x-axis. So I could project that vector down to the x-axis, and then horizontally we know it's going at root 3, or 2 cos 30. So we know the horizontal component of that vector. And we can do a similar thing vertically, and we'd end up with 2 cos 60, which is 1. And so we know vertical component is just j. So there's our vector broken up into its 2 components. So that's the idea we've looked at before, but there's no reason why we have to choose horizontal and vertical. You can project a vector onto any other vector you like. Let's have a look at this one. I'm going to project the u onto the v. Now, how do you do it? We drop perpendicular. So it's got to be perpendicular to the one you're projecting onto. So something like that. A way of thinking about it is, imagine you put a light source behind the vector and you're creating a shadow on this new vector. So the length of this new vector would be the length of the shadow. Well, because they will be parallel, because we projected at 90 degrees there, we know the length of that vector would be the same as the length of the third side in that triangle. Bit of trig we can work out it would end up being. The length of that third side would be the magnitude of our vector u, but times cos theta. That would be the scalar multiple of our vector. We now need to tell it which direction it's going in. So we'd have to multiply it by the unit vector in the direction of v, because if I multiplied it just by v, that would change the length. Well, we can put that into a formula. If I want to project u onto v, we'd end up with magnitude of u cos theta times the unit vector v. Well, there's an easier way of writing that, because we also know that u dot v would be magnitude of u times magnitude of v cosine theta. Rearranging that, I get magnitude of u cos theta, because remember that was in our formula we just created. That will end up being u dot v over the magnitude of v. Subbing that in, we now have this expression for the projection of u onto v. And notice the notation I'm now using. So that's how we do it. PROJ, obviously projection. U, the vector we're projecting, but then as a subscript we put the vector we're projecting onto. So v in this case. We end up with u dot v over the magnitude of v times, and this time it is times because it's a scalar we're multiplying, so it's not a dot product, it's a time, the unit vector v. But we can simplify that even more, because we had a formula to work out the unit vector v, and that was simply v divided by the magnitude of v. Well, on the bottom there, I've got these 2 magnitudes of v. They're both scalars, so I can multiply them together. So I end up with the magnitude of v squared. But we can simplify that even more, because we know the magnitude of v squared is v dot v. I just think this is an easier way to remember it. So we end up with u dot v over v dot v times v. Keep this in mind. Remember, dot product is not multiplication. So therefore, dot product and division are not inverses and they won't cancel. It's very tempting to get this v here and cancel with one of the vector v's in the bottom. But you can't do that, because this is a dot product as opposed to this being a multiplication. They're different things. So we need to leave it in this strange form, u dot v over v dot v times the vector v. A couple of things for when we're manipulating them. Lambda is a scalar, so you could multiply it by lambda first if you like, and then work out the projection, or work out the projection first, then multiply by the scalar. You'll get the same answer. And if you were adding 2 projections together, it's the same as finding the projection of the vector you get when you add them together. So projection of u plus v would be the same as projection of u plus the projection of v. Find the length of the projection. So make sure you read the question. It's not actually asking for the projection. It's that scalar multiple it's looking for. What's the length of the projection? Well, in that case, it'll just be the A dot B on the magnitude of B. Because remember, our formula would have been A dot B over the magnitude of B squared times the vector. Well, it's the unit vector now we're taking away because I only want the length. I don't want to multiply it by the unit vector. So be careful with that. It's so easy to put the magnitude of B squared on the bottom when you're finding this one, but it's just the magnitude of B. So if you just want to find the length. So A dot B will get 5 times 3 plus -1 times 4 over square root of 3 squared plus 4 squared. Good old Pythagoras. Another name for the length of the projection, you'll sometimes see it called the scalar projection. So if instead of saying what's the vector projection, they say what's the scalar projection, then that's what they're looking for, the actual length of the projection. Well, let's do an actual projection then. So we're going to project 2i minus 5j onto minus 2i plus 3j. So the projection of u onto v. So it'll be u dot v over v dot v times the vector v. So u dot v, 2 times -2, plus -5 times 3. On the bottom, well, even though I think of it as v dot v, remember I know it's magnitude of v squared, so it's basically sum of 2 squares, -2 squared plus 3 squared, but I'm multiplying it by the vector minus 2i plus 3j. So that fraction becomes minus 19 on 13. I'm just going to expand the whole thing out there, and I get 38 on 13, I minus 57 on 13, j. That'll do us for today.